All right, today there are a few main different things I want to do. I want to start off by talking about left and right hand sums and trapezoid sums again. And in this case, use Mathematica to help me do the approximations. You're not going to be required to know Mathematica right away, but it's probably worth taking notes on it because you will be doing this later in chapter 7 when we do some other numerical integrations rules called the midpoint rule and Simpson's rule. Second thing is I want to expand our repertoire of applications beyond motion, and in particular thinking about fluid flow, water flowing in and out of a tank in particular, still thinking about the fundamental theorem of calculus and how that's relevant. And then the last few things that we'll do is more integrals with substitution and a new technique called integration by parts. Okay, so let's go back to our example from last week that we started with, and that was the example of a speed and distance where we're given the speed and we want to find the distance traveled. Now let's go ahead and use the same example. It's a fairly simple example. The speed is little f of t is t squared, say in meters per second. Same example as last week. And the distance traveled from time 0 to time t, we'll call S is capital F of t. And yes, I'll say it once more, you could find capital F pretty easily by just doing an indefinite integral. In fact, I'll even do it up here. Do an indefinite integral of little f t squared to get, oops, sorry about that. All right, there we go. Do an indefinite integral of little f, which is t squared. You're going to get 1/3 t cubed plus c. And if you assume capital F of 0 is 0, that means c will be 0. But once again, I want to emphasize, for the sake of the second fundamental theorem of calculus, which is in section 6.4, and you should have read by now, that you can represent this distance traveled as a definite integral where the upper limit of integration is a variable. Integral from 0 to t of f of tau d tau. Use some other dummy variable like tau. I want you to make sure you make these conceptual distinctions. So we're integrating ultimately tau squared from 0 to t. What is tau? Again, it's just a dummy variable. I can call it anything I want. Okay. For the application, it still does represent time in a sense. Use the first fundamental theorem of calculus to get 1/3 t cubed evaluated from 0 to t. And yeah, when you plug in t and then plug in 0, you get just what you would think you would get, which makes you wonder why you're doing it this way. And once again, I emphasize you're doing it this way to emphasize the concept. And because if little f is more complicated, which we will consider more complicated examples, this idea of representing the distance traveled as an integral still works, even with more complicated examples. And you can still approximate the answers, even without a formula for the answers, by doing numerical integration. You can still approximate the integral. First and fundamental theorem of calculus are theorems. They're always true. First fundamental theorem is not always helpful, though, because you can't always find a formula for capital F. Let's approximate capital F of 2, the distance traveled from time 0 to time 2, with numerical integration. We did do this before as well, but let's review it again with something new now. I want to think about things a bit more generally so that we can program Mathematica to do the numerical integration for us. So this is going to be the integral from 0 to 2 of little f of tau d tau, if you like. You could use a t there because the upper limit of the integral is no longer a variable. Here's the setup. You want to get this down. You want to let A be your left endpoint. In this case, that's the lower limit of integration, that's 0. And you want to let B be the right endpoint. That's the upper limit of integration. That's 2. So A to B is your interval of integration. In this case, that's the closed interval from 0 to 2. This notation means take all numbers between 0 and 2, including the endpoints. That's the interval that we are integrating over. And what you want to do is you want to break up this interval from A, which is 0, to B, which is 2, into a bunch of pieces. And these pieces are going to be the bases of your approximating rectangles. Right? You remember doing that? Approximating the area under the curve with areas of rectangles. I'm going to pick some number of rectangles, n. N is going to be the number of rectangles. And I'm going to find the width of each rectangle, call it delta t, by doing the length of the entire interval, which is b minus a, divided by the number of rectangles. This will be the width of each rectangle. And again, I'm trying to set myself up so that I both understand the idea of what's going on and so that I can actually even program Mathematica to compute it for me in a way that I'll show you. So in this example, b minus a over n is 2 minus 0 over n, which is 2 over n. And I'm not specifying what n is. Excuse me. Why? Because I want to try different n's. And in fact, bigger and bigger n's and see if I get better and better answers. I should. If all those rectangles get skinnier and skinnier because there are more of them, their total area should approximate the area under the curve better and better. However, I can't quite stop here. I need to identify the different points that make up the different corners of the rectangles. The lower left corner of the first rectangle, imagine a first rectangle here. Actually, for our example, it would not look like that necessarily. The lower left endpoint is the A. I'm going to call that T sub 0. It's the starting position, so to speak. Then I'm going to go delta T units to the right, and I'll be at the point I'll call T sub 1. Then go delta T units to the right from that one and be at the point I'll call T sub 2. Delta T units to the right of that one, and I'll be at a point that I'm going to call T sub 3, etc. The B, the right endpoint of the entire interval, is going to be the last one of these T's. It's going to be actually T sub n. And the second to last one is going to be T sub n minus 1, and this distance will still be delta T. What I'd like to do to help me set things up in Mathematica is I'd like to figure out formulas for these T's in terms of A and delta T. It's not as hard as it might sound. T0, I've already said, is what A is. T1, look at the picture, is going to be the starting point A plus delta T, right? Just start at A, which is 0 for our example, but doesn't have to be 0 in general, and move delta T units to the right to get to T1. T2 is going to be A plus 2 times delta T units. Take 2 steps to the right, 2 times delta T. T3 will be A plus 3 times delta T. Start at A and move 3 steps to the right. And that pattern continues. T4 would be A plus 4 times delta T, etc. In general, you could call it T sub I, where I could be 1 or 2 or 3 or 4 or 5 or 6, etc. By the pattern, it's going to be A plus I times delta T. And for our example, A is 0, and delta T we found to be 2 over n. And this simplifies to 2I over n. The last one, T sub n, when I gets replaced by n in this formula, you get 2n over n, and the n's cancel, leaving you with 2, which is what B is. I already knew that had to happen. I said B was going to be what Tn is. but it's nice to see that it works out with the formula. So I'm now going to use a couple formulas in Mathematica to help me do numerical integration very efficiently. I'm going to use the fact that delta t is 2 over n, and I'm going to use the fact that ti is 2I over n. How? You remember left and right? Left-hand sums and right-hand sums. We talked about this some last week. In general, these sums will depend on what n is, right? I haven't told you what n is. I could pick anything I want for n. I could pick 1, 2, 3, 4, 5, 6, etc. Bigger n should give better answers. So the left-hand sum will depend on n. How does it go? Remember, with the left-hand sums, for each interval, you take the left endpoint. Like for the first interval here where I'm pointing, its left endpoint is t0. Take that and plug it into the function to determine the height of the first approximating rectangle. That'll be f of t0. If the graph of f goes through this point right there. Actually, for our example, it doesn't. It goes through the origin, but don't worry about it. In general, it might go through some other point. The second rectangle has its height determined by the value of the function at the left endpoint of the second interval, which is t1. Be something like that, etc. F of t0 is the height of the first rectangle times its width to give you the area of the first rectangle. F of t1 is the height of the second rectangle times its width to give you the area of the second rectangle, etc. I'm using the left endpoints for each intervals. For the last interval, the nth interval right here, I use its left endpoint, which is t sub n minus 1. Plug in t sub n minus 1 into f and multiply times delta t, and that's the area of the nth rectangle. I want you to start to get comfortable with summation symbols. This is a sum. You can write a capital sigma to denote the summation, and this is going to be worth doing for Mathematica's sake. We've got a bunch of values of f times a bunch of delta t's. The generic or general value of t that I plug in, I'm calling t sub I. The starting value of I here is 0. Then it goes up by 1 to 1. Then it goes up by 1 to 2. The last value of I is this last subscript, n minus 1. So I goes from 0 to n minus 1. Kind of a little strange there, but that is the case. With a right-hand sum, it's a very similar sum, except I'm using the right endpoints for the intervals. So for the first interval, I use t1 to determine the height of my approximating rectangle. That distance right there, from here to here, is going to be f of t1. For each interval, use the right endpoint to determine the height. So my first area, instead of f of t0 times delta t, is f of t1 times delta t. Then f of t2 times delta t, etc. With a right-hand sum, the last endpoint you use is actually tn instead of tn minus 1. F of tn times delta t. It's very similar. With summation notation, you now let I go from 1 to n now instead of 0 to n minus 1. Okay. Now we're about to go into Mathematica to program these things for our examples. We already know what the answer is, right? We already know what capital F of 2 is. Just plug 2 into there, you'll get 8/3. 2.6 repeating. That's the answer. We're trying to approximate it. It seems silly for a simple example to do it this way, but this generalizes to examples where you can't do it any other way. You've got to approximate it with summations instead of using the FTC. So I will share this Mathematica notebook later today, but it would be good for you to write some things down anyway. Let me get rid of this stuff here. First, some information about Mathematica syntax. When you're first defining a function, little f, you need to put an underscore after the variable name when you're first defining the function. Also notice you're using square brackets, not parentheses around the t. You need to use an underscore, and then don't use an underscore after that point. Otherwise, things will go wrong. So I'm first defining the function t squared. The colon equals could just be an equals. In general, I like doing a colon equals for some other situations that I'm not going to get into. Essentially, we're defining the function f of t by entering this. The semicolon is not necessary. It just suppresses output, although there would be no output in this situation, so it's not a big deal. Put your cursor somewhere on this line and do a shift return. Now it's entered. If I want to confirm it's entered, I could type f of t without an underscore and see it does equal t squared. I don't think I've defined a function g of t. If I type g of t, it just says g of t because I haven't defined g of t. I can evaluate f at numbers like f of 3 is 9, 3 squared. And now I can program these left and right hand sums. How? I could start this way. Left of n with square brackets, not parentheses, is going to be a function that I'm about to define that's going to give me the left-hand sum for any value of n that I want. What do I need to do? I need to effectively just use this formula here and replace the ti right there with 2i over n and replace the delta t right there with 2 over n. So I'm about to do that. Got that in your head? I'm about to use Mathematica's palette to put a summation sign in there. Let I go from 0 to n minus 1. Type this with ti equal to that, 2i over n, and delta t equal to 2 over n. That's what I'm about to do. How? Well, the summation sign is on the palette. I have the writing assistant here. You can get the palettes from the palettes menu. There are 3 of them, a basic math assistant, a classroom assistant, and a writing assistant. They all basically do the same thing, just organized a little differently. I usually use the writing assistant. If you go down under typesetting, this tab right here, and scroll further down, you'll see a summation sign, as well as integral signs, for example. Hit the summation button, and if your cursor was right here, then a summation will show up. It's this summation right here. That's what I'm about to type right there. So I type an I, then I tab over and type a 0, and tab over and type an n minus 1. So I'm matching what you see there. Then type f of ti. Well, you can't just type ti because Mathematica doesn't know what ti is. I know what ti is, though. It's 2i over n. Type in 2i over n, either by doing this. I can type 2i over n, or if you prefer, by using the palette to make a fraction and going 2i over n like this. Square brackets, not parentheses. Function inputs in Mathematica are square brackets. That's a good thing, actually, but it's different because otherwise it would be even weirder because parentheses could either mean distribute through the parentheses or it could be function arguments, and that would be confusing. So it's good to keep those ideas separate. Times delta t. Like the star means times. What's delta t? It's 2 over n. Hit the fraction button again and type 2 over n. Semicolon just suppresses output, which is not really necessary here, but again, I kind of like doing it. It also, in my mind, can help me separate, in a sense, different lines of code. What I'm about to do now is also define the right hand sum. And all I have to do is copy and paste this formula, say over here in the same line even, although it put it on a different, it tabbed down, change the word left to right, change 0 to 1, and change n minus 1 to n. And that will be my right hand sum. The trapezoid sum can be represented as a summation. That is possible, but it's simpler to think of it as the average of left and right, like this. Add left and right and divide by 2. That's a simpler way to think of it. Notice in each case, I'm using underscores to define the function. But once I've defined the function, I don't need the underscores anymore. In fact, if I use them, it would be bad. No underscore there, no underscore there, no underscores here or here. Once you've defined the function, you don't need the underscores anymore. So these are all entered, and I could now plug in a value of n. So for example, I could find left 2, right 2, and trap 2, for example. I'm separating those by commas and putting them inside curly braces. This is just going to give me a list of 3 numbers. The left-hand sum when n is 2, the right-hand sum when n is 2, and the trapezoid sum, the average of the 2 when n is 2. The approximations are not super great. Trap is okay, 3, but even that's not real close. The right answer, remember, is 2.6 repeating. Well, just to increase the value of n. Let me just copy and paste to save a little time here. Control C, Control V for copy. Let's increase n to 4. Should be closer, especially the trap. Unfortunately, it gives these answers as fractions. As a decimal, that is 2.75. Getting closer to 2.6 repeating. If you put periods after the 4s, decimal points, it will automatically do a numerical approximation. I also could have done, for example, / capital N at the end instead, if you've ever done that before. Let's try a bigger value then. How about n equals 8? Now trap's getting decently close to 2.6 repeating. How about jumping up to n equals 100? Yeah, it's pretty close. It still is off even with trap, just slightly off. I think if we went up to, well, for sure 1,000, you'd see all 6. Oh, it rounded the last one to a 7, which is appropriate. So it's getting better and better as n gets larger and larger. Better and better approximations. What do we call that even in Calculus 1? When you've got something approaching something else as n gets larger and larger. What's the name? Go ahead. Asymptotic. What's another name? Limit. Yeah. Can Mathematica do a limit? How about this? Huh, 8/3. It did it. That's the answer, right? 2.6 repeating. 2 2/3. Limit. That's pretty cool. Do the other ones work that way too? How about for right? Yeah, 8/3. How about for trap? 8/3. Yeah, the integral of this function from 0 to 2 is 8/3. Limits are still relevant with integrals. In fact, for this example, the function turns out to be simple enough that you can even find a formula for the left and right-hand rules in the trapezoidal rule. And you can see, looking at the formulas, that these things go to 0 or go to 8/3 as n goes to infinity. Look at each one of these things. The left-hand sum has two terms which go to 0 as n gets larger and larger. And you're left with 8/3. The right-hand sum, same thing. The only difference between these two is this one's a minus sign, that one's a plus sign. But they both go to 8/3 as n goes to infinity. And the trapezoid one's even closer because you don't have that last term. Still goes to 8/3 as n goes to infinity. Limits are still relevant. Do you need to be able to do it this way? Not without Mathematica's help, okay? Kind of amazing that you actually can find these formulas. You typically can for simple examples like this, though it's definitely not completely obvious how it happens. You need some formulas for some special summations, effectively, is the way Mathematica is doing it. But it's good to see that, yeah, I can look at that expression and say that goes to 8/3 as n goes to infinity. The limit of the Riemann sum equals the integral. In fact, you might even say that's essentially the definition of the integral, is that it's the limit as n goes to infinity of any kind of Riemann sum. Does that really work, though? You might wonder, if I made my Riemann sum really strange, would it work? The answer is, if your function little f is nice, like continuous, it will. So we don't worry about it. Can I clarify anything? Let's visualize this now. Visualizing the motion like we did last Friday. Oh, and why is it doing that over there? I don't know why that is up there. Let me re-enter something here. Oops. There we go. That's better. So what do we have here? We've got two graphs and we got a black dot. Just like we saw last Friday, the motion is going to be along the vertical axis. This is all one directional motion, right? The speed is always positive here. We're not talking about velocity. Which graph is the speed, the red one or the blue one? Little f of t was t squared. That was the speed. Which one is it? The red one. Yeah, you can check by imagine plugging in numbers. 1 squared is 1, the second coordinate at this point is 1. 2 squared is 4, the second coordinate at this point up there is 4. Yeah, the red one's t squared, that's the speed. The blue one is t cubed over 3. That's the distance traveled. Of course, the units for the outputs are different, so it's a little funny to graph them on the same set of axes. The units for the red are meters per second. The units for the blue are meters. Don't worry about the units. Focus on the concept of the relationship between these graphs. This is the actual motion upward. And you can see it's speeding up. Sorry, it's herky-jerky here. Wish it were smoother. It is speeding up because the red graph is getting higher and higher. The area under the red graph, let me pause this here. Say from 0 to 1.4, that's the integral of the red graph from 0 to 1.4. It's the distance traveled, remember? The distance traveled is the integral of the speed. the area under the curve. This area should be close to the second coordinate of this point in the blue graph, which is close to 1. Is it? It's almost a triangle with a base of 1.4 and a height of 2. Base of 1.4 and height of 2. Area of a triangle is 1/2 base times height. 1.4 times 2 is 2.8. Half that's 1.4. The area of the triangle that I'm drawing with the cursor here is about 1.4. Now our area under the red graph is smaller than that triangle. So our area's got to be less than 1.4, and it should seem somewhat reasonable that this area that's shaded is close to 1, the second coordinate of this black point on the blue graph. The distance traveled by time 1.4 is close to 1. I also made a little tangent line on the blue graph at that point. Since the blue graph is the integral of the red graph is the derivative of the blue. The red graph, the speed, tells you slopes of tangent lines to the blue graph. And when t is about 1.4, this red tangent line there at this point has a slope equal to the second coordinate up here in the red graph, which is close to 2. The slope of this line is close to 2. Does that seem about right? It's hard to tell just looking at it because, in fact, the scales on these axes are different. So it doesn't look visually like its slope is 2, but do rise over run. Imagine maybe moving this, letting t increase by maybe 1/2 unit. So this red line continues over here to t equals 1.9, right about there. The second coordinate goes up by about 1, from 1 to 2. Delta S over delta t is about 2 minus 1 divided by 1.9 minus 1.4. 1 over 0.5 is 2. Just did rise over run there for my imaginary line that I was drawing with my cursor. A line that's this tangent line extended further to the right. Change in t is about 1/2. Change in the second coordinate, s, is about 1 unit. 1 divided by 1/2 is 2. The slope of this is about 2. Same as the second coordinate of the speed at this point, close to 2. On Wednesday, I also want to relate this to another important concept called average value function, which then would be related to average speed and average velocity. But instead today, before we get into more about chapter 7, I want to emphasize that these kinds of ideas apply to wider situations. They do apply to velocity and position as well. Here's our other example from Friday. Now the motion goes up first, then down. The derivative of the blue graph is still the red graph, and the integral of the red graph is still the blue graph. The values of the red graph tell you the slopes of the blue graph. Like, for example, when t is 1, close to right there, the slope of the blue graph is close to 0, just like the value of the red graph is close to 0. Slope is positive when t is less than 1, just like the output of the red graph is positive. Slope is negative when t is bigger than 1, just like the output of the red graph is negative. The integral of the red gives you the blue. The integral of the red graph from 0 to 1.5 would give you the change in position, change in the blue graph, which is about 0. This area minus this area is approximately 0 because these areas are approximately the same. And this one contributes negatively to the integral because it's below the axis. Once t goes past 1.5, now this area is a lot bigger than this area. So you have a small positive area minus a larger positive area is a negative number, and the change in position is negative by that time. This also applies to flow rate problems, water flow, for example. This is going to be kind of a wild example. I'm going to have an example where my little f of t is 3 cos t plus 2 cos 3t. That's going to be my flow rate. Let me write that down. Flow rate, maybe net flow rate for extra emphasis, it can be positive or negative. It's going to be little f of t, let's say in liters per minute. It's a rate of change. I don't know why it's showing that. Was that always there? I don't know why that won't go away. It's a rate of change. It's the derivative of something. I guess it would be the derivative of the volume with respect to time. Liters with respect to t, to minutes. The volume itself in liters is going to be an antiderivative of this. And if your volume started off at volume 0, you could write this volume as the integral of little f from 0 to t. However, I want to allow the volume this time to start off at some other volume. Call it v sub 0. That'll be my initial volume. It's just a constant. That's the initial volume. If you add on an integral of the flow rate, that'll give you the total volume, the ending volume, you might say. Once again, to just throw a little wrench in things, this time I'm not going to start time at time equals 0. In this animation, which we're about to see here, I'm going to start time at time equals -3. Why? Because I feel like it. Just to illustrate that you can do it if you want. That's why. Probably makes more sense to start time at time 0, but you don't have to. You have freedom. Freedom in that to do what you want. Might be silly, but it still emphasizes the point. So I'm going to start time at time equals -3, and you can see the initial volume is whatever the volume of this blue water is. Red and blue water are mixing here somehow. It's just an animation. Don't take it too literally. The volume is whatever the volume of this is, close to half the volume of the tank. I guess if you look at the vertical axis here, it's the second coordinate at this point, which is a little bit bigger than 4. 4 liters, say. Time is going to start at -3 instead of 0. Just because I felt like doing it. It's okay. The ending time is still t. There's still a variable in the upper limit of the integral. And I still integrate the rate of change to find the total change. The net flow rate is a derivative. I could call this thing a capital F of t. And this would be in liters, ultimately. Now, V0 is the initial volume. This one is the change in volume, delta V, or if you like, delta F, because I'm calling the function F. Either way is okay. Don't be worried about the fact that I'm doing both of them. V is the dependent variable, F is the function name, but to represent the change in volume, I could either think of it as a change in the variable or a change in the function, it doesn't matter. Don't let it bother you. Those kinds of things used to bother me when teachers would do that. I'm just saying, don't let it bother you. It's okay. The second FT still applies here. The derivative of capital F is still, well, the derivative of the constant V0 is 0 plus the derivative of this integral. And it doesn't matter that the lower limit of the integration is not 0. It doesn't matter. The derivative and the integral signs still cancel each other out and give you little f of t. And this is true even for more complicated little f's like we have here. This is a more complicated situation. All right, we're about to watch an animation showing the relationships between these things. Run the code here. Maybe run it slow. Look for patterns. What do you see? Notice that the water level goes down when the red is going out. The water, so to speak, is going out. And it's going down faster when it's thicker. Like right now. That's water levels going down fast. And then when it stops and water comes in, then the water level goes up. The thickness of the red lines is supposed to indicate how fast the water is moving, so to speak, or how much water is flowing. The red graph is the flow rate. That's the little f of t in liters per minute. The blue graph is the volume in liters. If, for example, I let t start at -3 and go up to, oh, how about +1, right about here, the integral of the red graph gives you the change in the blue graph. What is the change in the blue graph from time -3 to time 1? The second coordinate of this point might be close to 4.5. The second coordinate of this point looks like it's close to maybe 7.8. 7.8 minus 4.5 is 3.3. Change in volume is 3.3. With respect to the red graph, these areas effectively cancel. They're about the same. See where I'm pointing? Those effectively cancel. So effectively, the integral is this area minus this area. And the fact that the integral, the change in the blue graph is about 3.3 means this area minus this area is about 3.3. You end up lower than you started, like right now, say, when the integral is negative. Now the areas that come from when the graph is below the axis outweigh the areas that come from when it's above. Effectively, these two areas cancel, these two areas cancel. And if you compare the areas here that are below the axis to the area here that's above, the fact that the graph decreases from time -3 to time 4 means these areas outweigh this area. They are more, they contribute negatively to the integral. It's not something you can get by just listening to me and then never thinking of it again. You have to take the time to think about these things as you read, as you work on problems. Maybe as you go to bed at night, think about it, okay? If you want, okay.